Hakan is a professor in the electrical and computer engineering department in Princeton. He did his PhD in physics at Yale, and he was after that a postdoc in ETH Zurich, and then also an assistant professor in ETH Zurich before he moved to Princeton in 2010. And full disclosure, Hakan's my postdoc advisor, my dear postdoc advisor, former, and I'm of course a fan of Hakan's physics. I can say that Hakan is as wholesome a physicist as physicists get, and he has worked in pretty much all nooks and crannies of QED and quantum optics, from lasers to many body physics, and more recently quantum information, superconducting circuits, cavity QED, you name it. So today we are going to hear more about the quantum information side of Hakan's research, and I can also I can say many things on the personal side, but I would say that I was very lucky to be Hakan's postdoc, learn physics from him firsthand, and it is an absolute joy that he brings to physics in general and to every discussion. One signature of which is that he's always running late to meetings, which is because his previous meeting has been going so engagingly, and it's a delight to work with Hakan, and I've been very fortunate to be his postdoc. And yeah, with that, I'd like to welcome Hakan here.
I don't think I need this, right? This part is private, so I arrived yesterday, and I had a lot of great discussions with a number of you, whom I see now in the audience, and also with Kanu and her students. And it's wonderful to see now the next generation pushing forward the frontiers with new problems that I watch from the sidelines and interest me a lot. So I think this is as gratifying as it gets for a person engaged in academic activity. So today, I'm gonna tell you about computing with physical systems. And we are going to talk a little bit about how to think about fundamental limits, at least one way to think about fundamental limits to computing. And we're going to focus on a particular corner of computing in this talk. This is my general new interest area. This is something we have been engaged in the last 5 years since COVID. But this talk is going to be specifically about data-driven inference, or in other words, machine learning side of computing, and physical neural networks operated in the quantum limit, in the quantum regime. And so the discussion will be about, maybe there's different ways to think about how we can productively use quantum systems for computing purposes. And so this talk is by design geared towards the younger audience here. So please jump in and ask. if something looks strange and doesn't make much sense, because none of the things I'm going to talk about today was obvious to us when we started this sets of projects. Okay. So here's a picture of the people who have been involved in the research that I'm going to be talking about in this talk. But I picked this picture because there's also Kanu. Some of you may recognize. This was, I think, the graduation sort of celebration of one of the students in the group, Said Khan. The names are the names that I've indicated. Those are the people who have been involved in the research that I'm going to talk about. Feng Junhu, who just graduated and moved on. Said Khan, Jerry Angelatos, and Marty is sort of the next generation who's still with me in the group. It's always a sad thing for me when people leave the group. You know, I don't like to let them go. Okay, so the same way, Kano. We had a really wonderful time. And so so there's probably a lot of people in the audience working in different corners of physics. I would say, Kanu here, you can get him excited about any type of physics, as long as it's physics in it. So, this is maybe another way, sort of broader umbrella of what I want to share with you, and that sort of focuses on what's going on in quantum computing today. You have some examples here from AMO and superconducting qubit systems, where we do really have systems level control and measurement capabilities. So we have moved on from individual components, quantum components, to really systems level control. Soon we're going to have 1,000 qubit systems, probably next year, if the plan goes well. That was put forward about a couple of years ago from IBM. But the understanding today and the acceptance, grudging acceptance today, is that before fault tolerance, we're not really going to see any practical use of these wonderful accomplishments. And I want to play devil's advocate there and say, well, we have these incredible systems, and can we think about new computational paradigms for such near-term quantum devices that embrace sampling noise, which is one of the big problems in quantum computing today, and finite coherence, and make something out of it and turn it into useful computation. So to answer a question like that, you need to first understand and be able to quantify what is the computational capacity of a given device with certain under certain conditions, like certain coupling to the environment, certain time of integrations, certain finite resources. How do we characterize this computational capacity of a physical device? And I will propose an answer to this in this metric that we refer to as resolvable expressive capacity. And then I think one theme that will also be apparent will be that really a dynamical systems approach to computing brings new perspectives in thinking about how you can use complex physical systems as computers. It doesn't need to be quantum, any regime. And so today we're going to be at least one question that I want to address is, what are the fundamental limits to learning? And by learning, I'm talking about data-driven inference with physical systems imposed by quantum theory. And I want to make this as concrete as possible. So first, Let me introduce physical neural networks, what I mean by physical neural networks. So on the left-hand side, you see a sort of a standard schematics describing a deep neural network. And for the purposes of this talk, you can think of a deep neural network as a mathematical transformation that takes an input u, imagine it's a long vector, high dimensional, and produces a output that is a function of that input u. And again, for the purpose of this talk, we shall divide this computation of this function u into two stages. The first stage will be, well, given this physical system with certain internal parameters theta that one would call weights, there will be, this will compute features of this function u. So each of these nodes is a feature, and we like to organize them into a vector. And that is essentially a transformation of this input u, which is parametric in theta. So in all this talk, I'm going to be looking at a case where these internal parameters theta are chosen. You have maybe optimized things. And so we are talking about the inference phase, where you want to now put inputs u and infer what the output function is, compute the output function. So then in the second stage, these features, you may ask, well, what is the space of functions that is spanned by these features, right? It's a function. You can think of it as a function living in this domain denoted by u. What is the space of functions that I can span by these features? So, and that is essentially this statement that I'm going to look at functions. Forget about this t-dependence. You can do this also in time domain. I'm going to think about what functions I can span with these weights. So these are just linear combination of these features. What is the space of these functions? That's one way of thinking about computing as a function approximation. What functions are accessible? Physical neural network, on the other hand, is a physical system that is subject to a physical stimulus, light. This is one example in the optical domain. So where the input u is now transformed into an output, a set of output features. These set of output features are generated by the natural evolution of this physical system. It just scatters. Maybe this is a nonlinear optical system, complex, has scattering in it. And then the features are essentially, let's say in this case, is this camera which has pixels. Each of these pixels is a photon number resolving pixel. Each of these pixels give me a record like this for a given input. And you can now clearly see one main difference between this way of generating features and that way of generating features. In this case, if you want to do computation on some input, that needs to be stored in the memory. And typically we think of a digital implementation of this transformation that is limited by the digitalization, right? Whereas in this case, the input may come from the physical domain, right? Something that comes from the environment and image. And the transformation is a physical transformation. The output features are essentially stochastic features, because typically, let's say in a photon resolving camera with each pixel, like this is x1, x2, and so on, as many as pixels, I do typically an averaging over a certain time interval, and my variables x bar are how many spikes I observe in one example, right? So these x's are actually stochastic features. And so when I find a w to approximate a function f, I'm really thinking about fuzzy functions. You know, they will be noisy functions because I've generated them out of noisy features. And we would like to understand what is the space of functions that can be spanned by these features generated by a physical system. So it turns out this way of thinking about computing, which I will call broadly dynamical systems sort of mindset in computing, it allows us to think about a broad range of computing systems and really expands what is meant by computing to a broad umbrella of physical systems. And one can probably categorize the animal brain within one of these domains in a simplified, model way, where, again, inputs, for instance, can come from physical domain. It's electromagnetic stimuli that are then transduced into electrical stimuli in neurons. And nowadays, we can measure the stimulation of individual neurons here in a massive scale. I can look at 1,000 neurons simultaneously and obtain their spiking records like this, neuron 1, neuron 2, neuron 3, and see how one input is encoded in the electrical stimulus distribution in the brain. Yeah. And an interesting finding that probably will connect now what we are trying to do physically is that even under identical conditions, and you can maybe realize the system not in a living cell, but as an input-output system in a beaker, right? Not subject to the constraints of human or animal homeostasis. If you think of it as an input-output system, there's now a consensus that even if I present the same stimulus, identical stimulus to this brain, this record, the features, will be different, widely different, not just tiny, okay? The same input, I show it a mouse, let's say here, the spike train will be very different in the next instance of repetition of this experiment, okay? No, it's because our brain, whatever processing system is really here, knows how to pick the robust features in this very complex stochastic sort of data by evolution and gives you a robust behavioral response. This has been again and again demonstrated in experiments.
So in some sense, there's fault tolerance built into it.
Yes, yes. So my neuroscience colleagues would explain this better, but it's a principle that turns out we have been trying to implement in a physical system as well. And we understand mathematically what that means. And so in that sense, for instance, a quantum system like a gate-based, vanilla gate-based quantum system, if you use it as a physical network, like I described before, where the inputs are parametric, you think of n qubits, the input enters as parameters of the unitary evolution of these things, and then you make measurements, and you do this 1,000 times, let's say 1,000 shots, and you construct a histogram, right? That's the standard way. The histogram is essentially about how many times, what's the frequency of observing a bit string 1111, 010. This histogram is exponentially large in this number of qubit space. This histogram is actually also a very stochastic quantity, okay? So, and even if before we average over S shots to generate this histogram, if you look at a single shot, the situation is very much like this. In a single shot experiment, I present the same input, I make a single measurement, and each if it's a large enough, 1,000-qubit system, no two outputs, measured outputs, will be the same, I guarantee you. Because the sampling space is so large, you will never get, again, the same bit strength. Which is also the problem of quantum computing today, that kind of sampling issue, okay? So all these systems can be described now really in terms of this function approximation idea, and one can reach some definitive conclusions about the space of functions that are accessible given a physical system with certain parameters and certain coupling to outside, and how many times you measure it. Yeah. So I told you one sort of the subtitle contained fundamental limits. And I want to be concrete about that. So one way I want to frame here a Gedanken experiment, which explains what I mean by fundamental limits. In this case, it's about fundamental limits in terms of energy of computing. How low in power, how low in energy can I get and still do a computation in a precise way? So this is, some of you know, if you understand a little bit circuits, this is a NAND gate, it's old technology, MOSFET, this can be thought of as a input-output system, which takes some inputs, like U1 and U2, let's say, and these inputs are encoded in voltage pulses of 0 or V volts, 1.5 volts, for instance, in certain encodings. And then, if you look at measure the voltage here between the ground and this part of the circuit, then this thing you realize is really a NAND gate. So for 1, 1, right? I should be getting actually 0 volts here. And so really this is a function generator, but this function is bit valued in the input and bit valued in the output, but at the end it's a physical stimulus that encodes this bit values, right? So I'm going to ask the question, can I still compute this function accurately as I decrease the voltage of 1, the bit 1. From 1.5 volts, I decrease it, and standardly you would think, well, if I get down to a level of voltage that cannot be distinguished from 0 with respect to the thermal fluctuations in voltage that I'd expect in this device, I should be making constantly errors here. And what if you make it now an analysis where you think of this as a dynamical system, and replace these guys with nonlinear oscillators of a model that take these inputs, which are time dependent, and see what they get out, and treat it quantum mechanically on top of it, then one can show that as input power is decreased for the encoding, maintaining computational accuracy, okay, forget about this part, but maintaining computational accuracy, let's say for this task, requires increasing the nonlinearity of these individual building blocks. And we can show this mathematically for a model oscillator system. And so as you can actually still generate this, generate this function, approximate this function, even if you cannot distinguish the input voltages anymore. And I will show you an example of a full calculation of how you can do that. It sounds like magic, but you can do it. But that's at the very end, if time remains. Otherwise, we can discuss it private. So now what I want to claim is this regime where I decrease the input encoding energy and increase the nonlinearity of these two oscillators is actually the regime in which we work with quantum computers. Okay? So if you take a standard gate-based quantum computer, which, as you know, we think of qubit, it has 2 states and so on. These are actually extremely nonlinear oscillators. They have all the other levels as an oscillator, but we try to make sure that during operation, the other levels are never occupied and you remain in the computational space, and that's quantum computing, gate-based quantum computing. And so now this brings us to what quantum computing is really. Quantum computing is really doing some computation at very low energies, where the input, which is u, which enters here parametrically, that value could be a gate rotation, right? A qubit rotation, yeah, theta angle of qubit rotation. But there's nothing about a pulse, microwave pulse that you send in that has a certain energy in it. And that energy is the angle of rotation. And so we are really operating in a regime in quantum computing where when I encode the input, it is exchanging single photons with these superconducting oscillators. And so that sort of is very close to an ultimate limit of energy. I just like to have this idea of how computing should be in quantum computing in terms of Shor's algorithm and Grover and variational algorithms. But I think this more general view is very powerful, as I want to discuss with you today. So let's talk about machine learning now. And the use of a standard quantum computer like this as a physical neural network. And I want to illustrate this with one way of doing this. This is not the only way. And with a very specific task so that we are clear on what we are talking about. The task is the classification so this is my input domain now, the vector u. This is now, it's 2 components, and let's assume that the inputs are coming from 2 probability distributions in a compact domain of u1 and u2. And so these probability distributions have come from one or the other spiral arm here. And when you ask for a u, it will come either from this arm or that arm. And you want to take that value of u that you have gotten and parameterize this Hamiltonian that this evolves this 4-qubit system, make measurements, organize these measurements into this output features, x, and then you want to find the w that gives you the function that assigns a 1, okay, to a 0 if u is coming from this domain and a 1 if u is coming from the other domain, okay? So this is a function way of thinking about this, a functional way. It's clear. And we will visualize this function now. This is really a function that lives in this domain. And so my target function or my ground truth function that I desire is f star, I usually denote, is this 0 or 1. And so the features, measured features, there's been different approaches to what should constitute the measured features. And it could be, for instance, the expectation value of the z, the expectation value of z for each qubit, and you can compose them into a vector like this. And then the machine learning way is you show a data from this probability distribution, you look at f, and you want this f, by the proper choice of w, to be almost as equal as possible to f star, which is this thing, yeah? And so the thing to be optimized here is w, okay? This is what we choose to optimize. And our metric is what we call capacity, and there's a reason we define it this way, but it's almost like the mean square error, right? This is the integral over all the inputs u that I've provided, and you want this thing to be minimum for the right choice of w. But for reasons, technical reasons, we look at 1 minus this quantity. And this is we refer to as capacity for this physical system to approximate this ground truth function f star by just optimizing these W's.
Just to clarify, the P1 and P sub 2, they don't have any overlap.
In this case, no, they can have overlap,
Can.
so that then you cannot do better than that overlap. It gives you an upper limit to what you should be getting here, what errors you should be getting. So this number in part, the C, if things are properly normalized, is a number between 0 and 1. And if C is 1 for that F star, then you have found a W that exactly gives you F star for all the inputs U. Then it's 1. And it's 0 if F that you can generate with the right choice of W lives in an orthogonal space to F star with respect to a measure PU. There should be a PU here, which is that input probability distribution. Okay. And if you then maximize this capacity for this F star that we desire, then the right W for a 4-qubit system generates this function. Okay, it's really 1 in these regions, 0 in these regions. Notice that we don't see, something weird is happening here, and that's because we don't have data there. The probability distribution is very small there, so it's making up what it likes. Yes.
It seems like that the capacity would not only depend on W, but also the way in which you transform from the choice of U to the Hamiltonian you apply to the system.
Absolutely.
So
but I'm going to discuss now the situation where that input, you found the best physical system, best internal parameters, best internal couplings that works. And we want to separate that optimization from this side for good reasons. We can discuss that. Yeah, you're right.
Excuse me.
Yes.
Clarification. What is the role played by linearity here? Is the state vector and, for that matter, a feature vector thought of as an element of a linear space?
Yes.
Necessarily.
Yes. So there are two functions of linearity. One is for some people in the community, optimizing only this W to make this function work is referred to as reservoir computing. Yeah. For us, this is a way to think about establishing a Hilbert space of these features X, and so that we can study this Hilbert space as a linear space of nonlinear functions, because each XU is a nonlinear function. As you see, U is in the exponential here, so it's a nonlinear function of very complex nonlinear function in quantum case of the input U. Yeah. And typically as in machine learning, you then have some test data, which is data that is not seen here, but drawn from this probability distribution, and then you test whether how well you do the separation of this data. And in this case, the classification accuracy is 94%. We have found that W that does it is really this function, and you see where it's going to fail and where it doesn't. All right. So now let me come to this idea of this question of capacity of a physical system and fundamental limits. So how do we think now about the function expression capacity? How many functions can a given physical system represent by just playing with W's? Yeah. And there's a very neat way of asking that question in this formulation. And that goes about this way. You first find the capacity, you come up with a set of orthogonal independent functions that live in this input domain, whatever it is. For each of these infinite set of functions, you find the capacity, find the optimal W, find the capacity, and then sum over all these functions. And the very nice, surprising result is that this, what is referred to as the total capacity here, is an infinite sum, is a bounded quantity, and its bound is L, where L is the number of independent measured features. So it doesn't depend on stuff in the system that you don't measure, okay? And this is generally an equality. So it's a very strong thing. This total capacity is an equality, unless you choose features which are related by symmetry and they are always the same, then you get an inequality, okay? So this is very interesting, and I want to show you concrete examples of how to think about this. So here we're going to look at how this capacity calculation is done for an n-qubit system by finding, these W's for a situation where input is coming from a one-dimensional input uniformly distributed between -1 and 1. Okay. So -1 to 1 is U. And now we are saying, okay, you remember, a nice set of polynomials that live in this domain that are complete and orthogonal is Legendre functions. So we say, okay, let's find the optimal W's for each of these to generate each of these Legenders. And here is the results, okay? And you see, this is the first 4, and there's a gap here. Then I plot 49 and 50. So you see capacity to approximate the exact Legendre, the zeroth order Legendre is 1, 1, 1, 1, 1, and then it gets lower, yeah? But if you sum up an infinite number of these things, it turns out it's equal to the number of independent features in your physical system. Yeah, that's the amazing result. I want to be, when I saw this result and what it implied, I was really I think it's something deep, yeah.
Sorry, one implication.
This is not our work, by the way. So I'm describing someone else's work from 2012.
So you're saying it's limited by the number of independent features?
Yes.
Is that upper bounded by anything? Increase the capacity?
That's about your dynamical system. You take a dynamical system, I can tell you how many independent degrees of freedom it has. For quantum case, we have an exact answer to that. This calculation we did. We just used the theory and confirmed that this bound really works. So this is this is good and bad, because it tells me that any physical system with the same number of independent measured degrees of freedom has the same capacity, which is not a very exciting thing for practical purposes. But we have known from experience that one physical system can be better than another system, even if it's the same number of degrees of freedom. So where is the catch? The catch, turns out, is in the number of experiments that you do. Yes.
Include dynamics?
Yeah, you give an input, you evolve, these qubits with that Hamiltonian parameterized for this input for a certain time t. Then you make measurements. That's all. Only at the end you do measurements, extract the features, then find the W's that give you this function and then this function and so on. Yeah. So there's dynamics, but it doesn't, it just gives you the final features, the end of the dynamics. Now, so this turns out is if you, for each U you give to the qubit system, parameterize the qubit system with, evolve it, and you make an infinite set of measurements. Infinite set of measurements. Whereas if you make finite set of measurements, the situation that you encounter is this. So this is a 1,000-shot experiment. So each value of U, right? I pick a value of U, I look at with the right W, what is the function value there, right? Each value of U, we do 1,000 measurements we construct our measured feature vector, which is stochastic, as in the photon case I discussed at the beginning. And if for 1,000 shot experiments, you get this best approximation for this Legendre function with capacity 0.89, 0.94, 0.88, and so on. And if you sum this infinite set of things, you will find a number that is not the L that you get here, which is then exactly what you want, because that will help you for given resources to tell which physical system is more appropriate here. And so this actually illustrates very nicely that keeping the resources finite, constraining the resources to be finite, and then optimizing is a well-defined problem. Whereas if you don't forget about resources, don't put a constraint, then it's an ill-defined problem. All the results about universal function approximation that you have maybe heard about and so on, that really is not useful in practice. Okay. So the question then becomes, can I say something about the total capacity for a given number of shots? And then I can choose my physical system, characterize my physical system, and so on. And that's what the story that I'm going to talk about today, that is mostly the results from this paper here, is about. So here I have to introduce how we use a gate-based L-qubit quantum system, how we use it as a feature generator, and then we think about functions that you can represent with these features by playing with this W. That goes to saying, what is the measured features I should be using? Should I use the expectation value of sigma z, sigma x, right? So it turns out a universal sort of set of such features is really the histogram. So you do S shots to generate this histogram, which tells you the frequencies of occurrence of each of these bit strings for a given U, right? Every given U has this histogram. And in practice, what we do is we take these things as one feature, the probability of what I get here as the second features, and so on, and we make a vector out of it. And then we shall try to find the best W that gives us a target function that we want. Is that clear? Okay. So we can prove that this gives us 2 to the power L independent features, because there are 2 to the power L different bit strings. And you can prove that it gives you 2 to the power L independent functions. Now, a very useful way of thinking about this is now in a high dimensional space of these features. So, let's say you have 6 qubits, you will have 64 of these features in a vector. Think about a 64-dimensional space. And I'm showing here the values that you get in the 64-dimensional space for a given U. One U is this, one U is that, one U is that, the other U is that. These distributions, they are the distributions that I get for each S-shot experiment. So this would be different values that I get for one feature for a given U for 1,000 shots. If I increase it to 10,000 shots, then the distribution gets narrower. Yeah. And you see, for every U, this distribution is very different. And so what we noticed here is that the noisy distributions themselves have a noise structure that tell us about the signal that we are seeking. So here, really, the noise contains if you know the structure of the noise, turns out you can actually do inference very effectively, even in the presence of output noise. Yeah. Okay, and here's one like slight result of the technical results in this paper. The main result is really an expression for total capacity of in this case, of a quantum system with L qubits that can be expressed. Turns out, right, let me remind you that total capacity is you pick a set of infinite set of functions that live in the input domain U, and you sum over the capacities and you get the total capacity. Turns out this total capacity has a expression that is independent of what function set you choose to generate that, to get that number. So it's a canonical quantity.
Question, a practical question about your 64-dimensional space. Does it come with an inner product or a norm?
Yes.
Notion of distance?
Yes.
Just strictly putting distance, no weighting of components at all, is that right?
The weighting, there's a weighting. The weighting is the probable distribution of the input. And so this total capacity is very interesting. It is a sum over 2 to the power L, where L is the number of qubits terms, right? For 8 qubits is 2 to the power 864 terms, where you have this structure where S, the number of shots that you do to generate this data, to do function approximation, enters in this particular fashion. So for S equals infinity, infinite shot experiment, this is the sum over ones, and you get 2 to the power 864. But this formula tells you when S is finite, how it is reduced. It's the answer to what we have been wondering about. And how it's reduced is encoded into these set of real values, beta k. And these beta k's turn out can be obtained as an generalized eigenvalue of 2 matrices, V and G, where V and G, B and G, can be obtained from the integration with the probability distribution of the measured features. They are quadratics of these measured features. X, X. Yeah. In this case, these would be the probabilities, right? X1 is the probability to get a certain bit string. X2 is the other bit string's probability. Okay, so now let me come to, this tells you something about, you give me your qubit system, you tell me how you encode the input, and I give you this number, and it tells you about the capacity to resolve how many functions it can resolve at finite shots. Yeah. But there's also something, it's not very practical. It's good for characterization of your physical system. But there's a practical side of it, which are in the eigenvectors corresponding to these beta k squared. And these eigenvectors turn out to be sets of coefficients that you multiply the features with, the weights, essentially, that gives you the highest signal-to-noise ratio functions. So the minimal error that is achievable. Yeah. We call them eigentasks. So instead of dwelling on the mathematical details here, I want to show how this works in practice, so that we can visualize this thing. This is actually an experiment on one of the chips in IBM. It's a 6-qubit chip, and we're doing a simple experiment where we draw inputs U from a uniform probability distribution between -1 and 1. Then we parameterize the evolution of these qubits with this U, and the way we parameterize it is shown here. And there is a reason we have chosen this encoding, which we will come later. But you see, this is how U enters. Okay, it's one of the RZ rotations. You choose these parameters, you fix it, and U enters this way. And one of the RZ encodings gets the information about your input. What I want you to pay attention to is this J here, which we'll come back to. J is a parameter that gives you the strength of 2-qubit interactions in this encoding. If I put J equals 0, then it's all single qubit gates. Yeah. So here is the probability of getting a certain bit string as a function of U, and that's essentially x1, okay, the first entry of my vector. And you see, as a function of U, this is quite a non-trivial function. This blue thing is the measured feature for 16,384 shots. And the other curves are numerically calculated, sort of what it should be. And you see they are very close. So these experimental systems are, are real. They really are close to what you theoretically would expect. And we can say more about this. And so what we're going to do is do experiments, draw inputs, get some result, construct from them these matrices G and V, calculate this beta k square and the total capacity. And so, okay. Now, total capacity as a function of shots is plotted here. Okay, it's a very busy plot. We'll come to this. These are the eigentasks that I told you about, this low signal to noise ratio functions of this system with that encoding that I described. So look at the total capacity. It starts by finding the distribution of beta k squares. And there are 2 calculations here, and they use different types of encodings. Yeah. So this is beta 1, right? This is the index of beta k. And they have this very universal form. Whatever we do, it's always in this form. So there's, and this is it's a semi-log plot. Yeah, I would like to note that. And so let's pay attention to blue first. No, to blue, yes. And then what we do is we take this beta k square and calculate the total capacity. And for a given number of shots, we get this value. We get that value. We get that value as the number of shots increases. Logarithm, again, exponent, it's increasing. This is a semi-log axis. So there's a nice rule of thumb here. You see when for beta k squares that are smaller than s, you can ignore this and it's a 1. For beta k squares bigger than s, then you can assume this to be 0. So s gives us a line here. You have to just sum over how many beta k squares you have here, and that will give you the total capacity. It's a rule of thumb. Yeah. So as you can appreciate, that this encoding is flatter, right? Its slope is smaller, so there's more beta k square here than this. And indeed, at a given number of shots, if you look at it, the blue curve gives you higher capacity than the other curve, the other encoding. Now, this is the ultimate total capacity, which is 2 to the power 6, which is 64. I made a mistake. 2 to the power 6 is 64. Yes, not 2 to the power 8. Yes. So this is the ultimate infinite shot capacity this system can reach. But we are lingering around here. So the question then becomes, what is this encoding and what is this encoding? You see, this gives me more total capacity at a given number of shots. And I will show you now that this encoding corresponds to an encoding that has some entanglement in it. And this encoding is one which is only like single qubit gates. And we'll try to address the question why entanglement is good in a concrete way. So let me come to eigentasks. So when you solve the eigenvalue problem I discussed, you can find these eigentasks. They are 64 in number. I didn't plot them all. And we are plotting every 4th eigentask. And there are 2 experiments here. One with about 1,000 shots, the other about 16,000 shots. You see with 1,000 shots, which is the fainter curve, you have more noise, right? But this is very small signal to noise ratio. as we go down in eigentests, these guys become more and more noisy. And that's the meaning. Beta k square actually gives me the error that is committed here when you divide it by s. Yeah. And this is one of the best functions it would be able to compute as a function of u, of the u that is drawn from here. It's interesting. I don't know. I mean, it looks like so now we have the beating heart of this system, and it tells us what this is the function. You know, I could approximate best for a given number of shots. Now, what other things does this insight teach us? So we have observed a strong dependence on this J, where J is the strength of two-qubit interactions. So we decided to study it. And I'm plotting here total capacity as a function of this coupling strength J. And what you find is there's a J, the total capacity starts out small, it becomes large, and then becomes small again. So it's not monotonic. But there's a J at which the total capacity peaks. So there is a ideal, there's an optimal two-qubit coupling that gives you a very high function capacity. On the lower plot, I'm plotting what's called the total, a measure of correlations in the output, total quantum information. And there are many measures, so we are plotting one of them. It's related to some tracing out of the qubit degrees of freedom. And this measure of entanglement, as you see, peaks at the same point. Okay, which is sort of it's not a proof, but it's an evidence that entanglement gives you more capacity at a given number of shots, and if it's properly used. But there's a caveat, you know, this obsession with entanglement. And forget about all these other plots. This is a theoretical calculation, not an experimental one, because we can go to here to 10 to the power 15 shots, and they would kill us if we had tried to do 10 to the power 15 shots at IBM. And so we are plotting here how my total capacity increases for a encoding that creates entanglement and for an encoding that has zero entanglement because it's single qubit gates. You see, the product state encoding gives you better capacity at very low shot numbers, which turns out to be a general fact. And we have some explanation for it. I'm not sure it's the right explanation, but we have an explanation in the paper. As you go to infinite number of shots, they go asymptotically to the same place. And what this plot to me indicates is that the benefits of entanglement really is clear only in the finite shot regime. So at any given number of shots, finite shots that in the intermediate regime that I look here, you see the entangled encoding reaches the theoretical infinite shot limit much before the product state encoding. Okay. Yes.
The product state encoded with no entanglement actually approach that asymptotic value.
Yes.
It looks as if it tops out.
It will, and I think one can show that actually asymptotically it will reach. So really the benefit is that entanglement gives you a benefit only for finite shots, is at least an anecdotal observation of that fact. Now you can ask, well, if I look at eigentests, how do the eigentests of entangled circuit and product circuit look like? Maybe do they carry a clue in terms of clue as to what is really happening with entanglement? What kind of benefit does entanglement give me? Yes.
I have a question in the previous slide, please.
Mhm.
So yeah, so in this plot, it seems that for small short numbers that actually the product states somehow outperform the ones with entanglement. So is there a reason for that?
Yes, as I said, we have a conjecture about this. It's in the paper, but I don't want to get into it here. Yes, there's probably a better answer. But it's a general observation. We always observe this. Yes.
Hakan, so do you assume some kind of feature for your inputs in order to calculate everything like IPC or eigentest and everything?
Do I observe?
Do I assume some kind of, say, independent inputs or some uniformly distributed inputs?
Yes, this is case for uniformly distributed inputs.
And following question is that what would you think if I have a specific test?
Yes, yes.
Different
Yes.
input distribution.
There it becomes really very interesting because it turns out the eigentests are independent of the number of shots. They are shot, they are quantities that live above finite shots. And their forms depend on the input distribution. So for a given input distribution, there is a certain functions that a given quantum system can approximate best. We do not understand how one can analytically understand, what this input distribution and what functions that you want to generate match to each other. That's one of our things we are investigating really. Yeah.
Thank you.
Yes. Thank you for your question. So looking at eigentask, if you look at the eigentask for correlated states encoding and product state encoding, you see that they are not very different from each other. Yeah, I mean, it's not that one is more oscillatory or more complex than the other. But what is happening is that in the product state encoding, the transition to noisy features happens much earlier. Whereas in entangled circuits, the transition happens much later. It's the flip side of the coin for beta k-square distribution being flatter. So the conclusion from this analysis is that correlations and entanglement, what they do is they give you, if you use it right, it gives you some way of canceling noise in the right way so that you get noise-free features. That's what it does. So now I want to, I think, I want to state some important application of these eigentasks, but not get into some theory around it. These eigentasks, as I said, why is an eigentask? Eigentask is just these coefficients that I should multiply each feature with so that I get this function y. And what I'm plotting as eigentask is this guy. And if I plot it as finite shots, it's noisy. Yeah. And an alternative way to think about these guys is that there's an optimal measurement basis. And this optimal measurement basis is a superposition with the same coefficients of these projectors. These are the bit strings, 0, 0, 0, 0, and projectors into bit strings. So you can think of this as an optimal measurement basis. And the way where eigentasks achieve practical relevance is that now I know that some of these guys are more noisy than others. So, and these noise is system dependent. And I want to actually, so what eigentasks give me is a way to do feature reduction so that I can throw out features that are much more noisy than others. Yeah, it just orders them, and I can throw out the ones that at a given number of shots gives you more noise than signal. Yeah, and so that truncation scheme turns out to be very powerful in practice. And instead of discussing what we did in that paper about this with quantum circuits, which is interesting. I want to give you some more recent work that we're doing where we applied this eigentask idea to optical systems. Yeah. And the idea, this is an idea where we believe, is going to be helpful in low light imaging or sensing. And one application is, for instance, a situation where you build an optical neural network, yeah, and that looks at a scene. And let's say in the scene you don't want to resolve this guy perfectly here, but you want to decide whether this traffic sign is 50 or not 50. Okay, a cross. Is it 50 or not? So it's the function that we want to generate is a 1-bit function. The result is yes or no. And so a general idea in estimation theory is that you can compress all this information here, and maybe you start out with many pixels here, but reduce it to, let's say, 4 pixels or just 1 pixel. And say, is this pixel above some value or smaller than some value? If it's above some value, it's 50. So you want to train the weights of these guys so that you can compress that information in a way that carries exactly the information you want. Yeah, and so this experiment has been done in Peter McMahon's lab at Cornell, and we loved it, and is part of our Murray team. But this was done before that, and we said, okay, so he did it at strong illumination. How low in illumination can we get and still do this? So I want to illuminate this scene with very weak light. So at any given time, I can read out here finite few photons. Can I do this classification? So it's this idea of low energy function approximation and so on. How low in energy can we go? And so what we want to do is, so we want to do essentially a technical name for this is we want to do feature reduction, which in this case is done physically, 4 pixels here. We want to do this feature reduction with eigentasks. And the way we are going to do this is that the information will be on a spatial light modulator, so apples, oranges, whatever. And we will shine a Gaussian beam on it. So that's our input, U. And it's a 1,000-dimensional vector number, pixels vectorized. It will go through a scattering medium. It will be recorded in an EMC-CD camera with thousands of pixels. So we will fix the integration time, and we will study, the accuracy of how classification of these guys with the number of shots. So 1 shot gives you 1 image, 2 shots give you 2 images, and we want to average, let's say, an S-shot image with very low photon count, get this very noisy image, and from that we want to be able to classify what is this. So this is done in this field using either PCA, principal component analysis, and you find the largest principal components. Then you give many examples, and we want to compare it to eigentasks. And so actually eigentasks turn out to look very much like PCA, so we wanted to understand the difference as well. And turns out eigentask is PCA in function space, not in fixed U. What we learned afterward. So the way eigentasks will work is that we will find all the eigentasks by just experimentation and showing many samples from the probability distribution of these things, and determine the eigentask by solving this eigenvalue problem, and then truncate these guys and do classification with a finite number of them. And so maybe 2, 3 eigentasks. So this will be very little information that you use to do classification. So here, I think we shouldn't belabor much, but technical side, this is what's called an MPEX-7 data set. where you get many, many samples of the same, thing. There are 70 classes, 20 image per class. And here we are plotting the accuracy that is achieved with this eigentask learning framework of truncation as a function of number of classes that you want to classify. And we are comparing PCA, low-pass filtering, and all the other feature reduction techniques to eigentask learning. I think the top curve is accuracy drops, of course, as we increase the number of classes. But what I want to attract your attention to is that this is really 2 shots. So we're just averaging 2 shots. This is 20 shots. And in 20 shots, again, still eigentasks deliver you equal or more advantage as a number of classes with respect to, I think PCA is the closest contender. But what we are interested in is this, where it's very noisy and we can do this. And so you can now ask, can I do this with 1 photon? Okay. And that's very interesting because 1 photon is the basis of 2-slit experiment, double slit experiment, right? You send 1 photon. Feynman has this nice discussion of, does it go from this slit or that slit? Let me close this slit and so on. But here we are asking the more general question of when 1 photon illuminates this guy or that guy or this guy on a spatial light modulator, can it carry information that can distinguish at the global scale these things? So finally, this is the last thing I want to show. What I actually here, in this case, you can visualize eigentasks. And eigentasks now here become filters that you act on the AMCCD camera pixels. And so this is eigentask number 1. Eigentask number 0 is normalization. It's not important. Eigentask number 1 is this, 2 is this. So it tells you that you should multiply these pixels with positive numbers, weights, these pixels with the negative weights, and these pixels are really not relevant. And then you will get the maximal information in terms of the classification tab. No, maximal information in terms of the input distribution. Yeah, and these sort of eigentasks, so many in number, you see they get noisier and noisier. This is what you'd expect. These guys carry the most of the information, and they look like drum modes, right? They look like eigenmodes. And that's not surprising because there's a spectral Laplacian behind eigentask construction. Okay. I want to stop here, but one thing I wanted to tell you is, share with you is, one may ask, I have this incredible quantum device, and if I think about this generalized way of doing computing, where would I see some interesting advantage? Where would I be able to do something that otherwise would not be doable with other classical means? And there we have, I think, a concrete sort of thing to say. We believe that these kinds of quantum physical systems, they are very good at machine learning inference on very weak, high-dimensional signals, electromagnetic signals. So just like, few photon illumination case and so on, and very high dimensional, you want thousands of modes. And this paper is a situation where one case where you have to encounter weak signals and you do some data-driven inference on these weak signals is readout of other quantum systems. When you have a quantum system and you do readout, you send a microwave pulse, which is very weak. It reflects and you look at the phase shift of this microwave pulse. So there's this, I think, a more general way of thinking about readout and sensing, where your reservoir or your nonlinear processor is in the coherently interacting with the quantum signal that you want to classify, learn about, and so on at a high level. And you can here show that this guy can do something that otherwise would not be possible. And we can point with our finger. And we have come up with a concrete example where this is indeed happening. This is a situation where you want to do quantum state discrimination on a quantum system consisting of two oscillators. Okay, linear, very simple. And so if you just scatter light out of these and look at the quadrature of light for two states which are created here, okay, of these two oscillators, and you want to discriminate, is it in this state or is in that state? So if you look at light that is coming out of these wires and cut it here and look at the measurement data, you will plot the quadrature plane of the microwaves here. You will find that this blue dots is what you would get in many experiments for one state. And these yellow dots are for the other experiment, other state. And what you see is that the mean of these microwave signals is the same, and the distinction is in the noise, okay? And in classical signal processing, what you would do is you would do many, many averages, and you would take the square of these signals, and then they would separate, and you would be able to distinguish them. But that is very difficult with these microwave signals because there's a lot of thermal noise that is added in the processing chain. This never works, okay? So the proposal is to put a physical neural network, what we call a neural sensor in here, and then read out the neural sensor that is subjected to this radiation. And if you look at now how the readout of this sensor looks like in the best plane possible for various conditions. If this system is linear, whatever you do, each of these classes overlap. So you won't be able to separate them, okay? The means of the outputs are the same as the means of the inputs. So any point, is stochastic version of the other state. So you cannot classify, but you can show that there is an ideal sort of coupling between them. And for a finite nonlinearity of the system, you can separate these two states and show on top of it that this classification accuracy is a monotonic function of this coupling strength between them. And as the coupling strength increases, right, you get classification accuracy close to 100%. And here we are plotting on the right axis the entanglement log negativity as entanglement measure between these two guys. And at the trends between these two are very similar. So you can see that entanglement is a critical exponent in this displacement and separation of these two states. So this is the only way to do this classification, state discrimination task that I know. And there's no classical analog of this thing. Classical analog in the sense that it should operate at the power levels that this thing operates with, is a single photon level. Yeah. All right, I think this is basically the end. I've introduced the people who have been involved, but we have collaborators in Princeton Computer Science, as in Tureci, and Raytheon BBN, Graham Rollins and Guillaume Roubaix, at IBM Quantum, Nick Brunn. And this is the larger sort of Muri team that all of us have been thinking about these set of ideas, and I would also like to acknowledge them. Thank you for.
Just more of a comment. When I see sort of analogs between quantum sensing, sort of looked at information theoretical perspective and quantum computing. So it seems like sort of the two sides of the same coin to some extent.
Yeah.
And I mean, you're probably aware of a lot of work which people have done using quantum information theory on quantum sensing, even for semi-classical states, so these eigen tasks you're talking about, they're like, for certain pure states, they can be the SLD operators on the probe states that you can get.
What operators?
SLD. SLD, symmetric logarithmic derivative operators. So
this is section that we found is really where these set of ideas will make a difference. So we're learning a lot of sensing these days. Going over past literature, it's a long history to it. And I think with these kind of new machine learning ideas, there's a new perspective that comes in as well. And in terms of, for instance, SLD optimization and so on, I can tell you that SLD is optimization techniques, if you are talking about the same thing, is not aware of the resources that are available. It's, it says, this is how you should measure, this is how you should prepare, and this is how you should couple. But, whether it's possible or not, I don't know, right, is what you saw. So now we do feel that whatever method that you will come up with to replace that has to be aware of resources. So it has to say, this is your dynamic range, blah, blah, blah. And so doing that optimization in a resource efficient way then becomes a nonlinear optimization problem, because the SLD business is linear problem. It's because it's in quantum domain, everything is linear and so on. So this is where we are now heading. And we definitely, I'm learning a lot from Saikat and others who have been involved in this business.
But like for certain problems, depends on the probe state approximations or assumptions. What we find with at least the Fisher information theory, and there's a Bayesian version of it where you can weight the P of U's, is that it's per in photon measurement information accurate. So it's kind of like with your bits or shorts. So the shorts equivalent in sense would be photons, and then you accrue at different rate. You can achieve the same limit asymptotically with your classical, or I shouldn't say classical, traditional measurement, but the rate at which you achieve that makes a huge difference practically.
Yes, which we find
which is similar.
Different sort of set of, absolutely. And we should later. I think that'd be great.
Okay, we have time for one quick question, please.
Yes.
So am I correct in understanding that in your imaging analogy, the eigentests correspond to the set of basically the optimal basis in which to decompose your map?
Yes.
And so
Decompose your measured results. So this is not a statement about Hilbert space before you made the measurement. It's after the measurement, after the QOVM, whatever basis you used, and it tells you how I should combine them linearly.
And maybe this is related to Daniel's question, but can you turn the problem around and ask, do I reconfigure the system so that the apple is one of the
Yes. Yeah, that's what we are trying to understand in terms of not just the ability to do so, but is there some mathematical framework where we can actually make arguments about what is best system without really an optimization problem that we do not understand. And I do think physical principles should be determining what are those set of physical principles. And just like we break down a very complex physical problems into little pieces and build up from there, there should be an information theoretic version of that. I think we are just scratching the surface of that, I think, beautiful set of questions.
Let's thank again.